right, Carlos, are they good?
Yep.
Okay, so my name is Kate. If any of you guys didn't know that, but this is our bridge design, Homie G's bridge design.
And my name's Wendy. We were required to build a bridge that was under $300,000, and it had to be able to carry a truck, and it had to be aesthetically pleasing. This is our first design, and it was $1,067,000, and it was aesthetic, but it didn't really work. This is our other design. It was still $1 million, and it worked better than the last one, but it was too expensive. And this is our third design. And it was $2 million.
They're going up somehow.
And it worked, but it was still too expensive. And this was our final design. It was under $300,000, and it worked better than all the other three.
Okay, decision matrices are basically used to kind of make a decision on which design is more appealing, less amount of money that we use to create it, structural stability. So we divided them into the 4 categories. So bridge number 1, obviously it was a really expensive bridge. $1 million is not something most of us or companies would be able to afford. So we rated all these in a 1 to 4 scale. So we gave it a 2 scale for cost because it was $1 million, which also was the cost for bridge number 2, so we rated them the same. Bridge number 3 was double the amount, was $2 million. So obviously that was still way too expensive. And somehow we got it down to under $300,000, which is why bridge number 4 we put as the highest scale for number 4, because it's under the constraint that Mr. Mendelburn told us to do. For structural stability, we kind of looked at which bridge would not deflect as much once the truck would pass over it. So for bridge number 1, the truck would pass over it and it wouldn't go down as much as bridge number 2 and 3. Bridge number 2 and 3 kind of looked like it was about to fall, so we didn't want that. Bridge number 4, besides it cost the least amount of money, it also didn't deflect as much, so when the truck would pass over it, you wouldn't really see how the load would make it bounce down. Resources, we kind of just looked at the materials used and how much of it we used. For bridges 1 to 3, we used a lot of materials, and it was a lot of members combined. Until we got to bridge number 4, it was only 20 members compared to the other bridges, which were 40 to 60. Aesthetics, obviously, the first 3 bridges were really long. They did look appealing, but not as the 4th one, which kind of had an arc. It was more appealing to the eye. So when we added up all the numbers, bridges 1 to 3 turned out to be a grade point scale of 8, while the last one was 19. Okay, research summary. So we basically researched what was the difference between the type of material that we used. We used solid bar instead of the hollow tube. So we chose solid bar mostly because it's less expensive. So obviously we wanted the money going to the bridge to be the least amount, and also it works better in tension. So we thought it would be a better idea to let it work better in tension. It was composed of carbon steel, which, as I mentioned in the past presentation, a carbon steel is composed of iron and carbon, and it's also one of the cheapest metals, so that contributes to why our bridge, we found it to be less costly than all the other ones. And our bridge was a reflection of the Warren Bridge, although the only difference would be that it has an arc, but the actual design itself with the triangles looks more similar to the Warren Bridge. And a consensus is a general statement teams use to be able to come up with an efficient solution to a problem. So we kind of reflected that in our design because we're trying to construct a bridge. So this was our final bridge design. As you can see, it looks like a little arc, kind of, so which we thought was pretty appealing to the eye. It looks nice. The compression and tension ratios for force and strength turned out to be 0.11 for compression and 0.071 for tension, which means that the bridge is experiencing about 11% of compression while it experiences about 7.1% of tension. And obviously we chose this bridge because it was the least costly. It was under the $300,000 requirement. It was more aesthetically appealing. And also we looked at the amount, but we kind of estimated the amount of time that the truck would have to pass over the bridge, because obviously if it took a longer time to pass over the bridge, it would mean that the bridge was not as stable as it could have been. So we also looked at that, and bridge number 4 was the one that took less time for the truck to pass over it. And also because since it took less amount of time, it means that it experienced the least amount of deflection compared to all the other bridges. And our references.
Where's the troll?
Did you guys get that video from somewhere? Did you guys make it?
We made it.
Woo, that's cool.
We thought it kind of went to our project because we passed over the bridge.
Extra credit.
Yes, thank you. Yes.
And do you want to share the bridge design of the bridge design?
Did you guys do this?
Yeah.
So basically, it doesn't take a large amount of time for it to pass over the bridge, which we thought was good, considering you don't want it to deflect.
Hey, you guys have to teach me to create that video.
And that concludes our presentation.
All right, give him a hand.